All right, we're going to pick up where we left off yesterday with these graphs and characteristics and plotting points and all that fun stuff. Help me out, though. Were we on number 3? Did we get to 4? Can you look? We're on 3. How far did we get on 3?
So the formula.
That was our quadratic, right?
Or the equation.
The equation? Okay. Did we do domain?
Yeah.
We did range?
Yeah.
What else did we do?
Slopes.
Various slopes. Okay. Is that all we wrote down?
Equation.
We did the equation?
Yeah.
H of x equals...
Negative x minus 1 squared plus 4.
Perfect. Anything else? That's it? Okay. There's a few more things I want to jot down about these quadratics. Let's see. There's another way to write out the equation of a quadratic. This is what's called vertex form because we got the 1 and the 4 from the vertex, right? Those transformations, those shifts. But what's another way a quadratic equation might be written? How might it look? It's called standard form. Ax squared. Ringing a bell? Plus bx plus c. Kind of look familiar? Yeah? Usually a, b, and c are numbers. Okay, but that's another way a quadratic might look. Notice how we have that power of 2. Okay? If a quadratic equation looks like this, there's a few things that we could possibly do to it, like manipulate it. We're going to talk about 2 of those. What's one thing you can do with a quadratic? Oh, man, you just told me your name, too. Justin. Sorry. Go ahead.
Foil.
You could, you mean the opposite of FOIL.
Yeah.
Yeah, it also begins with an F. If you FOIL something, you turn it into this. But if you want to go backwards, yeah, you factor it. Is that what you were going to say, Cameron?
Yeah.
Perfect. Okay. So you could factor a quadratic. It would turn it into those 2 like parenthesis groups. Okay. But what if factoring isn't an option? What else could you use? Yeah. Do we remember it? The quadratic formula? Parts of it? I'll sing you the song. I don't know if anyone's ever sang you the song before. Yeah.
Is it like opposite of b?
Yep.
Plus or minus?
Uh-huh.
Is it square root?
Yep.
4?
There's a 4 in it.
Yeah. I know it's over 2a.
All over 2a.
I just forget what's in the square root.
Go, Cameron.
Is it a squared or b squared plus 4ac?
B squared minus, can you guys see that, sorry? B squared minus 4ac all over 2a. Perfect. Now let's say you did all that. Remember, like a, b, and c are numbers and you actually calculated all that out. What would your answer represent? I think our graph looked like this before, right? Do you know what the answers to the quadratic formula mean? Okay, they represent x values, more specifically your x-intercepts. Okay, so looking at our graph, if we were to use the quadratic formula, we would get an answer of -1, and we would also get an answer of 3. Okay, we can see that from the graph. In this example, what would the factors look like if the x-intercepts were -1 and 3? Yeah.
X plus 3 and x minus 2.
Say it again.
X plus 1 and x minus 3.
There we go. X plus 1 and x minus 3. It's kind of the opposite of those x-intercepts. Does that look familiar? Yeah? So this is what the equation of the quadratic looks like in vertex form. This is what it looks like in factored form, okay, based off of those x-intercepts. Perfect. Have we ever heard the quadratic formula song? No? Do we want to hear it?
No.
No? Yes? Okay. Oh my gosh. The opposite. Oh, well, first of all, do we know Pop Goes the Weasel? Like bum ba dum ba ba da ba ba bum ba dum ba da da. Yeah? No? Okay. The opposite of b plus or minus the square root of b squared minus 4a and c all over 2a. Now you'll never forget it. Okay, or you'll have nightmares tonight thinking about it. All right. Anything else about quadratics you guys want to talk about? Anything worth noting? All right, let's try the next one. Go ahead and plot some points. This one's getting a little good. We have that undefined word in there. We'll eventually talk about it, but go ahead and plot the points that are easy for you. Alright, so if you were to play connect the dots, what kind of shape or graph would you have? Any guesses? Square root. Good. Square root. A square root is half of a parabola, like half of a U shape, just on its side. You see how you have that starting point, that vertex, and then you curve like a U? Okay, it's just on its side. So this is a square root graph. Now, what was a little tricky about this table was that undefined word in there. What do you think that means in terms of our graph? If something's undefined? Yes, Sierra? There's no value. Okay, so there's no value, but one of three things could be happening graphically, okay, signifying that there's nothing there. In this example, we literally don't have a graph. Okay, our graph doesn't go past that -3. So in this example, we just have no graph. But what else could show up on a graph to signify that there's nothing there? An open circle called, say it again?
A hole.
A hole, thank you. We could have a hole, perfect. There's something else that could happen. Everyone's favorite curse word, swear word in math. At least it was when I was in high school. Ass. Asymptote, right, okay. Asymptote. Asymptote. Okay, so if you see the word undefined in a table, one of those three is happening. In this case, there's no graph. We'll eventually see some examples of holes and asymptotes. Okay, so let's go ahead and write some things down about this square root. What do you want to tackle? Domain, range, what kind of slopes do we have? Do we want to figure out the equation? What do you want to do first? Domain, all right. How far left does our graph go? How far right does our graph go? -3 to infinity, brackets and parentheses, where do they go?
Bracket on the first one, and then parentheses on the next.
Perfect. Are we okay with the difference between bracket and parenthesis? We did that yesterday, right? Okay. What about range? How far low to high? -2 to infinity? Brackets or parentheses? Bracket, then parentheses. Perfect. Okay. Hopefully we realize if we were to shift that square root up and down, okay, or even left or right, that domain and range would change. But this is just the domain and range for this graph, okay, that we found here. Let's try to tackle the equation. Okay, this one's called j of x. So typically a square root starts at the origin, just like all the other graphs do. But notice how this one has been moved. We have that beginning point right there. So, based off the transformations, can we write our square root equation? What do you think? Can we first describe how it moved? How far left, how far right? Go, Justin.
Square root of x plus 3 minus 2.
Perfect. It moved left 3, down 2. Was it flipped at all? Do we need a negative in there? Probably not, right? We don't have a square root that looks like that. We also don't have a square root that looks like that. Those are all flipped. Okay, so no negatives. Perfect. Do we need a little number out front there? Okay, to figure out that number, we look at the initial slope between the first 2 points. What's that rise over run? Up 1 over 1? Right? So it's just a slope of 1. You don't have to write the 1 there if you don't want to. But realize if it was different, you would have to write that number. That's representing your vertical stretch or shrink. Okay? Speaking of slopes, if we were to do rise over run between all of our points, are they all the same? No, right? We have that various slope idea again. And since they're various slopes, that's what's causing the curvature. Okay, we don't have a straight line. They're not all constant. We have that curve. Anything else about square roots? Probably a big one. Can you take the square root of -4? Technically you can, okay? It's 2i, it's imaginary, okay? But you can't take square root of a negative number. We're going to deal with that idea this year too. All right, that's good with me if it's good with you. I'm going to try the next one, plot some points. If you were to play connect the dots, what kind of graph would we have? Exponential, nice. Exponential. All right. Is there something going on this graph that we could probably draw in or identify? I'm specifically talking about this left-hand side. What does it look like the graph is doing? What do you think, Zane? It looks like a flat line. So it's getting closer and closer and closer, flatter and flatter and flatter. Where do you think this left-hand piece is kind of leveling off at? What height? Good, Zane? 3. Okay, so that leveling off is kind of indicative of a horizontal asymptote. Okay, so exponentials have horizontal asymptotes. I'll abbreviate them HA. And this specific example has one at the y value of 3. Sometimes that may change, okay, but this one is at 3. Notice, though, how this horizontal asymptote is only on the left-hand side of the graph, not necessarily the right. Okay, so we may have different horizontal asymptotes depending on the graph. All right, what about domain and range? How far left does our graph go? How far right? What do you think? Good, Zane?
Argument is negative infinity, positive.
Okay, that's interval notation. What does that essentially mean? If you can have every single number as an x value? Go ahead, Cameron. All real numbers. Yep, they mean the same thing, so either one. What about the range? Low to high? Let's see, if I start off with my pen very low and I keep dragging it up, I don't really start to touch my graph until the y value of 3, right? But am I ever actually going to touch 3? No, because we have that asymptote there. So we would need a 3 with a parenthesis. And as I keep dragging my pencil up, it's just going to keep going forever and always because we have that arrow. So we'll go off towards infinity. Nice. All right, if we were to pick some slopes here, constant or various? Various, definitely. There's a big curve to this graph. All right, let's go ahead and try to tackle the equation. Before we do that though, are we familiar or do we remember what a general exponential function looks like? Kind of where different numbers are located or where the variable is? It can be tricky. Okay. Usually it looks something like this. AX or A times b to the x plus c. It's called exponential because your x is located in the exponent spot, okay, exponential. And what we're going to try to figure out are what are these a, b, and c values. Now, this c value is actually representing where your horizontal asymptote is located, because you know if you add something on the end of a function, that's what causes it to go up and down, right? Typically, the horizontal asymptote's on the x-axis, but notice how ours was shifted up 3. So in this case, the c value, we would need a plus 3 on the end. What we're going to try to do now is figure out what's the a and the b. And this is where we're going to have to get a little, not creative, but we may have to do some guessing and checking just to make sure it works. We're going to go ahead and take a look at some of the numbers in the table. And I don't know about you, but the easiest number pair that jumps out at me is this 0, 4, right? Okay, so if we were to plug in 0 for this x, our answer would have to eventually be 4. Same thing going on here. If we were to plug in 2 for this x and then add 3, our answer should be 7. So we need to try to figure out what's this base number that we would need in order to get this table of values to be true. So do we want to just guess some numbers? Can we start with these ones? What do you think, Jared?
2.
You just want to start with 2, or did you know it was 2?
I feel like it's 2.
Okay, how did you know that?
Because 2, well, it showed me 0.
Uh-huh.
0 to the x power is 1 and then plus 3, 4.
4, good. Okay, so if you plug in 0, 2 zeros is 1, anything to the 0 power is 1, plus 3 is 4, that checks out. And then go ahead, Jared.
2 to the second power.
Uh-huh.
Plus 2 is 7.
Okay, 2 squared is 4, plus 3 is 7. Looks like it checks out, right? If we tried 4, 2 to the 4th, we got 16. 16 plus 3, we got 19. Looks like it's checking out. So in this case, what's our a value? If it's not really written out front, what's it understood to be? 1. Okay, so our a value is 1. You don't have to write it there if you don't want to. Now, this figuring out the b value is a little tricky. You may have to guess some numbers and try them out, but eventually you'll find it, okay? So there's the equation of this exponential function. Now there are two ways we can classify exponential functions. Do you remember what those names or classifications might be? It's usually exponential blank or exponential growth and decay. Is that what you're going to say, Zane?
Yeah.
Perfect. Okay. Do we know the difference, or how can we determine if an exponential graph is classified as growth or decay? It's okay if we don't. No? All right. Exponential growth, you know you read a graph from left to right, okay, just like a book. Exponential growth is when your graph moves away from the asymptote. Decay, however, it moves towards the asymptote. So in our example, is this exponential growth or exponential decay? As you read or trace the graph from left to right. Growth, right? Okay. What if I changed it a bit? What if I did this? Is that one growth or decay? As you read it from left to right, are you moving away from the asymptote or towards it?
Away.
We're still moving away. Okay, it's still growth, but you're just growing in the negative direction. Okay, you're growing down. Decay would, if I erase this one for a second, decay would probably look something like that. You see how as you trace it from left to right, you go towards the asymptote? Okay? So it's all about where your graph is in relation to that asymptote. Anything else on exponentials? No? All right. Let's check out our next one. Plot some points for 6. We can only really plot 3 points, right, based off of the graph we're given. So if we were to play connect the dots, what does that one kind of look like? Let's see, maybe if I were able to plot the negative 11, it would look something like that. What kind of graph do we have? It's actually another exponential. Remember before in the last one I kind of drew one like that? Okay? It's an exponential, it's just going downward this time instead of upward. So if it's exponential, that means it has a horizontal asymptote somewhere. Where is that on this one? Good, Zane? At 2. Yep. Okay. So let's tackle domain and range for this graph. How far left, how far right? Patrick, you got an idea?
It's all real.
It is all real numbers. Good. Okay. What about range? How far low, how far high? Good, Zane?
Negative to infinity and 2.
To 2, yep. And parenthesis on 2 because we have that horizontal asymptote there. Perfect. All right, so since this is another exponential, all the properties we talked about for the last one apply to this one. Is this one exponential growth or decay? As you trace it left to right, it's growth, right? This one's growing just downward. Okay, it's moving away from that asymptote. Let's try to tackle the equation. Let's see. A times b to the x plus c. Let's try to figure out those values. Is there an easy one we can write in right off the bat?
Plus 2.
Plus 2, yep. All right. So this one's going to be a little tricky. Okay, you might have to guess some values. If you were to plug in 0, you should get negative 6. If you were to plug in 2, you should get negative 30. Okay? Personally, I would start off with this base value to help you out. You can starting with 1. Hopefully we realize starting with 1 probably wouldn't be a good idea because 1 to any number is what? Still 1. Okay, so you're not going to get anywhere with 1. Let's maybe try 2. If 2 doesn't work, we'll try 3. If 3 doesn't work, we'll try 4. Okay, we'll keep going. Let's go ahead and try 2. Let's see. 2 to the 0 would be 1, right? And if we were to add 2, we would get 3. Is that what we want? No. Okay. So maybe there might be a value for a out front. In the last example, it was 1. We didn't have to worry about it. But let's maybe see what would happen here. If 2 to the 0 is 1, what could we multiply 1 by and then add 2 to it to get negative 6? Can we think about that? 1 times what plus 2 would give us negative 6? What do you think, Zane? Okay, maybe we'll write that out mathematically. 1 times something plus 2 should be negative 6. What do you think, Cameron? Negative 8. If we subtract the 2 over, we would get negative 8. Let's go ahead and test this, okay? Because now, if we plug in 0, we're going to get our answer of negative 6. If we plug in 2, we should get negative 30. Let's check it out. 2 squared. We got 4. 4 times negative 8. Negative 32 plus 2. Negative 30. Checks out, right? Okay. Now, if you had a calculator and you wanted to check some other ones, you could, but it looks like we got a little lucky choosing that 2 there, okay? If that second point didn't work, you may have had to go back to the drawing board and maybe choose 3 as your base. Exponentials are a little tricky because you have to guess and check some numbers, okay? Anything else for this exponential? No? All right, let's check out the last one at the bottom. This one's a little different. Okay, go ahead and try to plot as many points as you can. All right, so you realistically can only plot 3. I plotted, though, the negative 1,000 and 1,000 just to give me an idea about where they might be. Okay, but I know that's off our graph. Again, we're finding out that we have some of those undefined pieces. What did we say might be happening graphically if that word shows up? 3 things, or possibilities rather. Go, Jody. No graph. Could be a hole, or it could be an asymptote. Okay. Let's maybe see if we can narrow it down, okay? So at -3, does it seem like there's no graph there whatsoever? I don't know about that, because clearly we have graph on the left and clearly we have graph on the right, okay? At 1, I don't think it's no graph either, because clearly we have some graph on the left and some graph on the right. Okay, so we can probably rule out no graph. Let's go ahead and check out a hole. At -3, if we have this little graph here and this little graph here, does it make sense that we could just put a little circle there? Do we see how if they're very, very close together, you see how this is -1.25 and -1.249? Aren't those extremely close? It's like they're so close together, but there's just a little chunk missing. Okay, that's what's causing that hole there. So at -3, that's what would be classified as a hole, because really close to the left and really close to the right, they're practically the same number. There's just a chunk missing. What do you think is going on at 1? Because if we look to the left, that's a really high positive number, and if we look to the right, that's a really high negative number. Yeah. That's a vertical asymptote. Perfect. Okay. So on the left-hand side of 1, we are extremely positive, and on the right-hand side of 1, we are extremely negative. Can we see the difference, like on the table between hole and asymptote? Holes, the numbers are really close together. Asymptotes, they're extremely opposites. Okay? Now let's see if we can graph the rest of this. So for this -1,000 over here, I can probably connect that little piece. And then if I look on the right-hand side, from the hole, I know I have to go through that point I plotted, but I can't go past that vertical asymptote. So I have to go up in order to connect it to that arrow I drew previously. On the other side of the asymptote, I have to be going down, but as I travel to the right, I have to connect that point all the way out there at 1,000. Is there something else we can draw on this graph now that we have those lines or curves drawn in? Does it look like there's something else we can identify? There's a where? Good. Yes, we have a horizontal asymptote at -2 on the left, but now we also have a horizontal asymptote at -2 on the right. Okay, in this case it's happening on both sides. Remember, for exponentials it only happens on one side. Perfect. So that one's a little tricky. You really have to analyze those undefined ideas, but also what's happening around those undefined locations. Are we doing okay? Make sense? All right, so here's the kicker. What is the name of this type of graph? I saved the best for last. It's a tricky one. It's called a rational function. Does that word sound familiar at least? Okay, rational function. Let's go ahead and tackle domain, range. I think clearly we know we have various slopes because our graph is curved. And we'll try to tackle the equation. What do we think about the domain? How far left do we go? How far right do we go? But we have to be careful about any of those undefined spots in the middle. What do you think, Justin?
Negative infinity to 1, union 1 to infinity.
All right, definitely 1's in there. We've seen the U's before, right? Those unions, okay? So you're telling me I can go from negative infinity all the way to 1, and I can touch every single point in between there. Is there a particular location that I can't touch? I like the 1, but there's another one. -3, right. We can't touch that hole. Remember, it's undefined. There's nothing there. So negative infinity to -3, union -3 to -1. Good. Are we okay with that? We got to be careful with those holes and asymptotes. All right. What about the range? Let's see. If I put my pen down below and I drag up, when do I initially kind of hit something that's a roadblock? -2. All right. So negative infinity to -2. Can't touch -2 because it's an asymptote. We're going to need a union because clearly we have more graph. Now, if I start at -2 and continue to drag up, don't I kind of hit my hole again? Where is that hole located on the y-axis? Maybe you can use your table roughly to help you. -1.25. We'll say that. That's okay. It might be -1.2499. Okay, but relatively close. I'll take that. And let's see, that should be 2. Sorry. -2 to -1.25. All right, union -1.25. So if I start from the hole and then continue to go upwards, I no longer have any more holes or horizontal asymptotes to worry about. So that would be infinity. That one was a doozy. We had multiple sections. Okay? All right, last but not least, let's try to tackle this equation. Rational functions are always fractions. So you're going to have something up top and something down below. And the fact that we have a hole and an asymptote going on is going to help us write this equation. What's important about a fraction? What's the one thing you can't do? Yeah. You can't have it over 0. That's a no-no. So we're going to use those undefined spots because that's telling us those are the numbers that make the bottom 0. So if -3 makes the bottom 0, it makes it undefined, what would that factor look like? We need an x. What do we need to cancel out a -3 to make it a 0? Like a +3. This is x plus 3, right? If you were to plug in -3 right there, wouldn't that make it 0? And 0 in the bottom's a no-no, okay? We also have another undefined spot because it was an asymptote at 1. So what would the factor look like there? -1. Perfect. Okay, so the undefined spots are telling you the factors in the denominator. Now we have to try to figure out what if we have factors up top, okay? So I might be having you dig deep for this one, but what is special about a hole? How can you tell based off of an equation if something's a hole or not? What do you think, Sierra? If it cancels out. So if this x plus 3 came from that hole, we would have to need an x plus 3 up top, right, in order for those to cancel. So if you have a hole, the factor in the denominator must cancel with the same factor up top. So we know that there's an x plus 3 up top as well. An asymptote, however, does not cancel. So we cannot write an x minus 1 up there. Okay, there's just an x minus 1 down below. Now, there could be another factor. Actually, there is one, but we're not going to talk about that here. Okay, we're going to talk about that in our first unit. Okay, so for now, we'll put a question mark, but we'll eventually talk about how we can get that other factor. Are we doing okay? So far, so good? All right. You guys are lucky. We're going to save the unit circle for next week. Okay?